All right, I think now it's good. Um, let's get started with a little bit of what I was doing last time, because I know technically I'm supposed to start a little bit with the FE solution today, but I want to do a little bit of code because this Friday we don't have Python lab, we have the normal lab. So I want to do some code. Before I do the code, I will put you on the spot and I'll have you write some pseudocode and then I'll code it. But I think some of the challenges with coding things are obviously some of it is related to syntax in Python. So some specific errors that you can get with writing Python versus MATLAB. But even before that, I think that the abstraction of seeing something that you would be able to do by hand and then trying to put that in pseudocode is maybe even more important than the actual part of writing the code. So what I would like you to do is go back to the notes from Monday about the so you should go back and check the table for 2 points. Is this 2 is minus 0.57 and plus 0.57, and the weights or the width of the rectangle is 1. Do the following. So this is, I'm gonna creating a new page. Today is 8th, I think. Let's just say lecture 8.5. So what if I ask you compute integral or approximate integral using Gauss quadrature and the function that I wanted to integrate is from 3 to 5. I want you to integrate, let's say, x cubed plus x squared plus x plus 1. So I want you to compute that integral. But what I want you to do is I want you to write the pseudocode. So what will you need to define? What variables do you need? And then sort of the steps that you will need. If there's a for loop, where do you put the for loop? And ideally, I think this pseudocode should work for any choice of a number of Gauss points. That's better than just saying 2. Should work for ng Gauss points. So it should be a general code so that if I say ng is 2, then it should work with the 2 Gauss points. If I say ng equals 3, then it should work for 3 Gauss points, and so on. So what is a general way of structuring the code so that we can program it? I will program it, you won't program it today, but I want you to do the pseudocode. So I'll give you maybe 7 minutes to go about it, and then I'll come back and I'll code it. You can ask me questions, then you can talk to each other. Yeah. There was a Peter. It's not around. There was a Peter sequence over here.
But if you're saying this, if you're trying to do something, it's like, this is somewhere else. So if you are playing with
Could be a function.
so your part is complicated enough. Whatever, make that work. You can double check this out.
And then I'll write the code. If you want to write the code, then I'll also write the code. Yeah, I just want to have you go from the theory to how we will actually compute in a general way for the recipe, so that it's not just this example. So maybe you can go and evaluate how does it work for a general case. Yeah. All right. Let's give it a go. I'll probably do it in the code directly. So let's do that. And hopefully we can follow your pseudo code. Stop sharing here. And let's start sharing here. Actually, I already need import NumPy. I already have a Python notebook on the I already have a Python notebook on the Brightspace, but I'll redo it here from scratch. The main thing that we will need later on is going to be, let's do some function definitions. This is what I was telling Andrew. There is this function that we need to evaluate, right? So let's just have it here. This f of x. And that one, in this case, given x, I should return this polynomial, right? So x, I don't know if I have the +1, but for example, that one function that I need to define and encode this, that's it. And so that if I call that function with some value x, it will return whatever the value of the function is for that x. That's one thing that I need to evaluate. So the function that I need to evaluate. Then the other thing that I need to evaluate is the, I call it the isoparametric map. That one takes xi and gets me x. Given xi gets me x. Now, this one depends on the element. So if you remember, this has a plus b over 2 plus xi times a minus b minus a over 2. Right, so that was the map. Now here I'm using a and b, which I haven't defined, but that is the map. So this, I make usually a distinction. So this function is a function of xi that gives me x. These a and b are some parameters that define, so typically I will pass it in an extra argument. That's typically what I would do. Again, because the main takeaway here is that the isoparametric map given xi gives me x. So it is a function of psi. These a and b are just the parameters. They are some variables that should be defined somewhere, but they are the map is not a function of a and b, it's a function of psi. So I would usually say this is parameterized by a and b, but it's not a function of a and b. Okay, so that's the other thing that I need to define. And then in this case, it can be a function or it can be a variable, just a variable. So the Jacobian, for the linear map, the Jacobian is just a constant, right? So the Jacobian is just a plus b over 2. Sorry, b minus a over 2. That is the Jacobian. It's just a constant. But we will see that if you want a quadratic map, then it is not a constant. So this is just the same as before. Jacobian of the map. Is the derivative. So just to be consistent with the notation, I'll make it a function of psi with some parameters. Again, this is just a number, but just to keep it consistent. That's it. So these are the three functions that I need. That's it for the functions. Okay. The other thing I need is I need the table with the Gauss points, with the different Gauss points. I don't want to do array with Gauss points. So you can do, let me just call it GP. I will use a normal array. I will not use a NumPy array because the size changes with each row. So for the, it's gonna be three nested things. So for the 1 point Gauss, the location is just 0 and the weight is 2. Then for the 2 point Gauss, locations are minus 0.577 and 0.577. And the weights are 1, 1. For Gauss 0.3, maybe I'll do it like, you can do this to split lines in so this is 1 Gauss point, and it's the point time comma weight. This is 2 Gauss points, it's points array, weights array. For 3, it is, I have it open here. So 2 of them are here. So this 0 and so well, minus this 0 and plus. And then the other one is the weights, which is I think 5 over 9, 8 over 9, 5 over 9. Yes. Again, this is the same structure, but just for 3. And I'll stop right there. See if it doesn't complain. It did complain. Why? Oh, because it doesn't like the comment here. Guess I cannot do this. This actually, what can I not do this? Oh, it has to be empty. There we go. Okay, it does allow me to split the lines, but Again, this is just the table. It would go on forever. If you want a bigger table, it would continue. And now finally to the main part of the code, which is, I saw the group over there had an if statement to read a particular row of this array. That could work. This is just one option. Actually, the way I have it in the current code in the Brightspace, I don't have this. I actually have different GP. I have like a GP1, and that one just has basically this information. I have a GP2, which has the 2 Gauss point rules. Could be separate arrays for given. That is okay. This is just one way. This is not the only way. The main takeaway is that you definitely need some way to store the location of the Gauss points and the corresponding weights. And now what do we need to do to evaluate the integral? If you remember, the integral looks something like integral equals sum over I of f of x of psi at the integration points times the Jacobian times the weight of the integration point. This is what the what in the theory it looked like. It was a sum over integration points. Maybe I should say IP, right? Sum over integration points of f of x of psi, where the psi is the what I read from the table times the Jacobian times the weight of the integration point. So this sum should mean for loop. So when you see a sum like that, you should immediately think for loop. So what we are going to do is we're going to do a for loop. I'm going to call it IP so that I match the same. And how many times should I do this loop? Is basically my degree of freedom. It should be this ng. So if I ask for 2 points, for example, then it should do it twice. If I ask for 1 Gauss point, then it should only do it once. If I ask for 3, then it should do it 3 times. So it depends on how many Gauss points you have. So for a given for loop, I need to evaluate f of x of psi of IP. So these are nested functions. So the first one that I need to evaluate is x of psi. And I have that is the isoparametric map. Right? So that one is just evaluate this guy. I need to define my parameters. So I need to evaluate the isoparametric map for a given psi. I'm going to call it psi IP. I still need to read this from the table, and I still need to define my parameters. But this will evaluate this x of psi. Now, given that x, now I can evaluate f, right? So now I can evaluate f so that I don't overwrite. Let me just do psi IP, FIP. Otherwise, I will overwrite the name of the function. It's just called f. So this is basically calling the function that given x, and then maybe some parameter, it will give me the value of the function. And then I also need to evaluate the Jacobian. So that one is just the Jacobian function, x param. And then I add to the integral. To add things to what we should do is we should start with 0 and we should add to it. So I equals I, so that we continue adding to the sum. I plus j times f times the weight of the integration point. This is still not complete, but we still have some missing pieces here. But does this piece of code make sense? I need to loop over the integration points because I need to do that sum for each integration point. I need to evaluate my map and the Jacobian. I need to evaluate the function that I need to evaluate, and then I need to add up to the integral. Those are all the things that I need to do. Now, what are the things that I'm missing here? I'm missing, they are underlined. I am missing param. That param is basically what defines my element. That one I need to define as well. So param equals AB, where AB are, in this case, I think I said, I don't remember what I said. What were A and B? 3 and 5. So for this particular element, A is 3 and B is 5. Okay, so now I've defined param. Now that is not underlined. There's still, oh, this should be XIP. There's still two things that are underlined here, this XIP and this WIP. So the value of the Gauss point and the value of the weight. Those are in my table. So I just need to read them from the table, right? So I just need to read. So XIP, I just need to read from my table. And that one, which row of the table should I read? I should read the row corresponding to the number of Gauss points that I want. So if I say I want, well, I should actually be, it's going to be a little bit annoying, but I need to subtract 1 because the indexing in Python is from 0. So if I want 1 Gauss point, I should read the 0 row. And if I want 2 Gauss points, I should read the row number 1. I know it does, it's just that Python starts from 0 for the indexing. So row 0 means 1 Gauss point, row 1 means 2 Gauss points. So this will read the corresponding row. And then which column should I read? The corresponding IP column. So what this will do is, in the first time of the loop, it will read, depending on what NG is, we can print it. So print do integral for here, NG Gauss points, currently Gauss point IP. Right, so this will print, you know, if I define NG equals 2, which is what I did there, it will do the loop twice. So this will print doing integral for 2, Gauss point 0, doing integral for 2, Gauss point 1. And then this is what I'm reading from the table, and the WIP is, I should say, I wonder if I did this correctly. Now I feel like I might have made a mistake. I made a mistake in how I arranged my table, but we'll see. I think this is going to be correct. I think I made a mistake arranging the table. So psi equals psi IP, and then weight equals weight IP. Oh, this should be weight IP. All right, let's see if this runs. I made a mistake. Let's see. This is interesting tuples. Obviously, it doesn't like me. Do I need to do? This? Let's see if it needs this. Okay, read the first one. And then if takes one position argument, but two were given. So what did I miss? Oh, F does not take parameters. Sorry, F does not take parameters. F just takes X. All right, there we go. So you can see I'm reading the corresponding row. So in this case, because I asked for 2 Gauss points, the loop is repeated twice. For the first time that it goes into the loop, it says, I'm doing it for 2 Gauss points. The first Gauss point, so 0, has psi equals something, weight equals something, and it's just reading the table. So it's just reading this value from the table and this value from the table, the other point with the other weight. And then given we can print more things, but given the psi and the W, evaluate the map, the Jacobian and the function, add up to the integral. Yes? You don't in this case, but if you think about it, the map is a map from psi to X, right? The isoparametric map. And the Jacobian is the derivative of that map. So technically, it is a function of psi. It's just that if the map is linear, then the derivative is just a constant. So it's not really a function. I mean, it's a function, but it's a constant. But if you just think of it in abstract way of the isoparametric map is some function of psi that gives you X. The Jacobian is the derivative of that function, which is a function still of psi. It's just that for linear case, the derivative of that linear map is just a constant. So it's really not a function. Other questions? Yes.
I was trying to follow along with this. For some strange reason, it's about this line.
So isoparametric map should be defined with taking two things. So, yeah, it should take, yes. Yes. Yep. And so, for example, if I change the NG to 1, let's say I change NG to 1, then it will only do the loop once, and it will read only the first row of my table. So if I do it with 1, it will only do the loop once, and it will only read that row of my table. So it will only read psi equals 0, W equals 2. You can see that even with 1 point, the integral is not that bad, 170. With 2 points, it was 173, 178. With 3 points, it will do the loop 3 times. And it's basically the same. Right, so with NG, now the loop is repeated 3 times. And you can see that is this psi and W, this is just reading the three rows of that table. And then just again evaluating the isoparametric map, the function, and the Jacobian, and adding to the integral. Questions? I'm gonna guess that this is the actual value of the integral. I don't know what the value of the integral is, but should be that. Couple of things for this. You can see that we are integrating the function, even though it was some function of X, we're integrating by with this change of variables by integrating something in the -1 to 1 range. The more points you add, the more accurate your solution is. But you can see that, you know, as you add points, you get a little bit more accurate, but you don't get that much more accurate. So at some point, you basically don't get more accurate. And is this easier than trying to compute the integral by hand? Definitely, because this works. If I change the function or if I change the limits of integration, it will work. So if I say, I'm not interested anymore in this function, I want a different function. So I just do, you know, some other function. So x minus 1 plus 2x squared, whatever. I just want another function to evaluate. This works, right? So this will just repeat the same steps. It will just, when it goes to this evaluate f, it will just evaluate a different function. Same for, this is general, right? So this works for this element between 3 and 5. If you have another element that is between 1 and 2, for example, it doesn't matter, it will just evaluate the function between 1 and 2. Because in any case, this isoparametric map is going to be mapping whatever a and b are to the -1, 1. So this is what I mean when, you know, coding it in this way is more general, more flexible. When you have a different function to evaluate a different element, the code is exactly the same. All we need to change is some of these parameters. Sorry? Yes, there is. We're not going to do it here. We're going to do it all derivatives by hand, but there is an automatic differentiation in Python. I think that's the main thing. And I'll upload this code. There's already some code in the bright space. I guess I ended up taking pretty much all of the class. So I will just, we're gonna have to the final element interpolation next week. I'll just give you a little bit of a preview of what we are gonna end up doing on, and why is this important? I would say two things. One is there's two reasons why we should care about doing numerical integrals, well, three reasons. One is in case you ever need to do any sort of integral in the future, then you can just approximate it with code. Second, just to get you to think about how to transform some equations into code. I think just general programming skills are useful with Python. And the third is because doing integrals is central to the finite element solution. So again, just remembering the map of what we have seen this far. We have done strong form to weak form. We have done how to approximate functions. If you remember, the weak form looks something like that. So it has some integrals. So we will need to be doing these integrals, right? And we are not going to compute those integrals exactly. We are going to compute them with Gauss quadrature. So all we need to be able to do is evaluate these things. If we can evaluate these things, that's it. We will have a function that says evaluate dw dx and a function that is evaluate du dx. Then we have a loop, and then we'll do the integral. Now, a little bit more details. If you think about what the UH looks like or what the WH looks like, we also figure out a specific way of interpolating functions that uses these shape functions, right? So that we said the U of H is not any U of H, but is actually this sum of this Ni of X times the value of Ui. And the same for the weight functions. This is just a different representation, which we'll talk a little bit more about on Monday. And so this will change things a little bit from what I did today. What I did today, I had a f of x, and I just put some polynomial. And in the future, when we care about the u of x, UH of x, or the derivative of that, it's not any UH or any derivative, it's gonna be of this form, right? So it's gonna be using the shape functions. And if you remember this, we talked about last week, why do we do it this way? Because the U of H could be whatever. There's so many possibilities to what the UH could be. And by defining these shape functions, then we always have the same shape functions, and the only freedom that we have is just the movement of these UI values. But we don't need to worry about how to represent different functions. We just code this def n1, def n2, def n3, depending on linear, quadratic, or so on. And that's it. And we reuse these functions all the time. We don't really need to create different functions. We'll just repeat using the same shape functions and the derivatives. So that's why we did it that way. Anyways, we'll do that on Monday of next week. We have a lab on this Friday, but this is where this is going. When we put this into the weak form and we do the integrals, we are going to end up with the stiffness matrix and the force vector. So we'll do that on Monday and Wednesday of next week. Yeah, we'll end up here, but I won't talk about this today. Let's stop right here, and then I'll let you go early, and then we'll talk on Monday. Stop recording.